Thank you for joining us on Synthesis Workshop. On today's Research Spotlight episode, I'm very happy to have with us Dylan Holst. Dylan completed his undergraduate studies at the University of Florida, where he worked under the supervision of Professor Ronald Castellano, focusing on the synthesis of hydrogen-bonded pi-conjugated oligomers for organic photovoltaic applications. Currently, he's a fourth-year graduate student in the Wickens group at the University of Wisconsin-Madison, where he works on the development of alkene functionalization reactions using the dication pool electrolysis strategy. And from there, I'll let you get started, Dylan. Thank you very much for joining us today to talk about your work.
Thanks so much for the introduction. So today, I'm going to be talking about some work that I've been doing in the Wickens group here at UW-Madison. I'm really excited to talk about it. Okay, so I'm going to start my talk today by talking about alkenes. Alkenes are perhaps one of the most useful functional groups actually in organic chemistry. You can think about doing a wide range of different transformations on them. You think about doing oxidation or reduction or radical addition or coordinate them with a metal. There's a lot of stuff you can do. In particular though, there's one type of reaction that I think is somewhat actually underrepresented in the literature despite its usefulness, and that is the oxidative vicinal substitution reaction of an alkene. So what you can do in this reaction here is you can imagine taking some kind of terminal alkene, for an example, and taking a typical nucleophile here that I'm denoting by this HX, and in the presence of some kind of oxidant that actually renders this process thermodynamically feasible, you can get to these really useful vicinal difunctionalized products. And so the reason why I think this reaction is really powerful is because you can think about taking alkenes which are widely available, both in natural sources as well as from petrochemical cracking, and then combine them with widely available nucleophiles to generate these really valuable products here, just as an example. And this is really resulting in a rapid increase in molecular complexity, something that I think is really amazing that you can achieve with this type of transformation. So if there's a way that we can introduce diverse oxidative vicinal substitution to the synthetic lexicon, this would be really, really enabling for the synthesis of complex molecules from really cheap and abundant precursors. Typically, rather than including some kind of external oxidant, traditional vicinal substitution reactions that are used today will actually incorporate this oxidant into one of the reagents that you're trying to functionalize the alkene with. And this is actually just a direct result of electronics on these reactants. So if you think about the alkene, these are typically going to be inherently nucleophilic. And so in order to render this process actually feasible, you're going to want to pair this inherently nucleophilic species with some kind of electrophile. So what this typically looks like here is a selection of reagents that are used for this purpose. You think about peroxides or molecular bromine or these electrophilic fluorine reagents, aminoiodinanes, etc. These are reagents that have been activated by introducing this oxidant portion that renders these reagents electrophilic so that they can undergo reaction with the alkene. And so these are really useful, and they have been incredibly useful, in fact, for a lot of transformations, especially you can think about oxygen atom transfer. You can think about doing an epoxidation on an alkene. This is something that we use a lot in organic synthesis. But these kind of electrophilic reagents can start to actually become limiting on things that you can introduce. Specifically, if you would think about Aziridine synthesis, kind of in contrast to epoxidation, there's a lot more challenges associated with this. So we can kind of think about the ideal Aziridine synthesis. What would be the most useful transformation here is you could take some kind of alkene and some kind of nucleophilic primary amine and then put them together to create an aziridine. And aziridines in themselves are incredibly useful molecules because they can undergo a wide range of nucleophilic opening reactions, which can then give you access to really diverse and complex secondary amines. So typically what this is done traditionally is with, as I mentioned before, these electrophilic nitrogen reagents, specifically here, established in the 90s, Dave Evans, the aminoiodinane precursors for aziridine synthesis. These are really good at forming these aziridines, but unfortunately, these have required this additional stabilizing electron withdrawing group, such as a Tazla group, in order to kind of strike the balance between reactivity and also the reagent stability. And so this is a problem because if you're thinking about if we want to create diverse aziridines, we want to be able to actually tolerate alkyl groups on the nitrogen as well. And this is actually a problem that a lot of groups are working on. Specifically, some recent examples that I want to highlight are some work from the Leonori group last year. In this process, they actually can undergo in-alkyl aziridine formation, this time via photoredox catalysis, actually generating a amine radical cation in situ, which can undergo radical addition to the alkene, and then from there go towards the aziridine product. And here they're actually able to introduce alkyl substituents in a way that previous aziridination procedures have not been able to. And then outside of that, actually developing additional electrophilic nitrogen reagents and kind of introducing these to not only aziridination reactions, but other types of reactions as well. Bill Morandi has worked on this as well. Another recent paper last year came up with these really elegant sequences to introduce a wide variety of different electrophilic nitrogen reagents, such as having an alkene or a cyclopropane or even a halide on these electrophilic nitrogen reagents. This has really, really expanded the competent nitrogen substitution reactions in aziridination and other related transformations. And these are very substantial developments in this area. So kind of just to summarize this, the traditional aziridination reactions that are employed today still use these reagents in order to pair with that nucleophilic alkene. And despite their advances, these are quite limited actually to electron withdrawing groups on the nitrogen. And there's only, in fact, less than 10 unique alkyl nitrogen substituents on these molecules. So we were wondering, is there a way that we can expand the ability to introduce diverse alkyl substitutions on these aziridines? And so rather than activating this nitrogen reagent, we wondered if we could actually activate the alkene instead, getting into some kind of vicinal dication equivalent. This time activating that alkene, we can actually think about introducing a simple primary amine here rather than an electrophilic nitrogen reagent to form these aziridine products. And if you can pair this with what has been shown previously with electrophilic nitrogen reagents, where we have less than 10 unique alkyl substituents, well, this would give us access to over the 1 million commercially primary amines that are available. And this would be substantially improving the access to alkyl aziridine products if we could achieve this. And so we were really interested in this idea. So we were wondering, is there a way we can actually generate this vicinal dication synthon from some kind of alkene? And if you think about it, the most obvious vicinal dication synthon that we can think of is perhaps the dihalide, something like a dibromide. These are really accessible easily from the corresponding alkene doing a simple dibromination reaction. I mean, you could imagine just taking the dibromide and then stirring with some amine, perhaps with a base, and get the aziridine product quite easily. We actually tried this reaction using a wide range of different conditions that we found in the literature, and we were never actually able to observe that aziridine product, and we observed only elimination to this vinyl bromide product. And this kind of problem actually attracted the attention of Sharpless in the late 80s. So he came up with this really elegant sequence going from some kind of alkene, subjecting that to this osmium catalyzed dihydroxylation procedure, then stirring with thionyl chloride and then sodium periodate and ruthenium catalysis, getting to this cyclic sulfate molecule here. And then taking this molecule, subjecting it to amination conditions, and then followed that by ring closure, either with butyllithium, sodium hydroxide, or even LAH, to get to these alkyl aziridine products. And then furthermore, there's actually another sequence that's actually used industrially, especially in the synthesis of ethylenamine, doing an epoxidation reaction, then ring opening, and get to the similar intermediate here, which then can undergo a ring closure reaction to yield the aziridine product. So this is kind of the most robust method to get to these alkyl aziridines from the corresponding alkene, but as you can see, it takes quite a sequence to get there in many cases. And so we were actually wondering, is there a way to really get to a more reactive vicinal dication synthon without the need for multi-step procedures? And the way we were thinking about doing this was actually going more towards an actual dication. It turns out that getting to a actual dication or a cation is actually not as crazy as it sounds. So I want to talk now about Yoshida's cation pool method. This is really an amazing procedure that actually can generate these really reactive cationic species in solution. And this is through electrochemical oxidation of some kind of substrate. Through this electrolysis, you build up these reactive intermediates in solution, typically at really low temperature, and then turn off your electrolysis, add a nucleophile in a second step. This has been used not only for N-acylaminium cation pools, but also for oxocarbenium type reactions. And this has been really successful for introducing not only oxidatively sensitive nucleophiles, but also generating these highly reactive intermediates in very cleanly through the use of electrochemistry. But he did observe a problem. Sometimes you can get too reactive. So if you get to a benzylic cation, he found that no matter what temperature you went to, these would always decompose. And so his solution here was actually to add some kind of stabilizing group that could intercept that really reactive intermediate. So now you have some kind of stabilized cation pool, which then has attenuated reactivity such that you can still intercept it with a second nucleophile without decomposition. This is really successful. What he used was this sulfilamine stabilizing group, which could react with that benzylic cation, but then was still reactive enough to undergo a subsequent nucleophilic addition. And he actually showed a wide variety of different nucleophiles were competent in this process, especially ones that were oxidatively sensitive. And so we were really inspired by this method. We wondered if we could generate a dication in this way and then stabilize it, but still have it react with a second nucleophile, in this case, an amine, to generate an aziridine. But if we're thinking about oxidizing an alkene, for example, a terminal alkene, this oxidation is going to be prohibitively difficult. Already for that first oxidation, we're thinking about over 2 volts versus SE, which is way above many common functional groups on organic molecules. And then that's just the first oxidation. We don't know how difficult that second oxidation is to actually get to this vicinal dication. And even then, this vicinal dication has to be long-lived enough to be built up in solution. And so we weren't hopeful for a direct oxidation. We were really impressed with these early disclosures from Henry J. Schein, started out in the 70s, of this reactivity of Thianthrenium radical cation. What he did here was take these thianthrene radical cation salts, and then these would undergo a reaction with an alkene to form these 2 different adducts with that alkene, where you either have one of those thianthrene molecules attached to that alkene. In this case, we call this the monoadduct, or you have the addition of 2 of these thianthrene molecules across that alkene, which we call the bis adduct. We were really inspired by these dicationic adducts because these presumably would be highly reactive towards nucleophiles. So what we imagined here was, rather than the oxidation of the substrate, we could oxidize thianthrene instead, have that react with our alkene, generating our stabilized dication pool in this case, and then turn our electrolysis off and then add a nucleophile to generate these aziridine products. And taking an alkene, undergoing oxidation in the presence of thianthrene to generate our dicationic adducts, which will serve as electrophiles, our vicinal dication synthons, then introducing the amine after electrolysis is complete in the presence of some kind of base to generate these aziridine products. And so if we wanted to validate this dication pool strategy, we needed to answer a couple of questions first. So the first thing we needed to figure out was, can we generate these electrochemically? Are they well behaved electrochemically? Can we actually do this adduct formation step with one of these alkenes? And additionally, we needed to validate, can they actually undergo substitution with a nucleophile in a distinct step, in this case, an amine. So to answer those questions, we first looked at the electrolysis of thianthrene with the simple alkene for phenylbutene. In this case, what we've been employing here are simple carbon electrodes under a constant current setup with acetonitrile as our solvent, and then tetrabutyl ammonium hexafluorophosphate as our electrolyte. And as you can see, when we subject these conditions to electrolysis, we see a beautiful purple color that is really, really satisfying to see every time. That purple color is corresponding to the thianthrene radical cation that's being generated at the electrode. And then we observed, what is our yield of these mixtures of mono and bis adduct products? And we were able to show that we can indeed form these. And not only can we form them, we can actually characterize them via X-ray crystallography. So these are actually stable enough to be characterized this way, and we were able to unambiguously identify that we do in fact have this mixture of adducts here under this anodic oxidation. can actually do these reactions under constant current and still get quite high yield of these mixture of adducts. We can also employ a commercially available DC power supply, in this case doing constant cell potential, and we get a comparable yield of these. And then actually, despite their presumable reactivity, this adduct formation stuff is actually quite robust. So not only open to air, but also with the addition of exogenous water 1 equivalent, we still see quite high yields of these adducts being formed. So this adduct formation step is quite operationally simple. And so we're able to validate that we can form these adducts electrochemically, but then we needed to look at their substitution. So we took a mixture of these two adducts and then exposed them to a combination of benzylamine as our primary amine nucleophile, as well as cesium carbonate as our base. So all we did here was just run the electrolysis, get our mixture of adducts, and then turn off the electrolysis, and then just add these second reagents to that same solution. And then we observed a high yield of the desired alkyl aziridine product. And then excitingly as well, following that substitution of these adducts, we return almost all of our neutral thianthrine that was contained in those adducts. So we were really inspired by the initial findings into this robustness of this method. And so then we wanted to move on and see what kind of amine substitution we could tolerate in this aziridination reaction. So to reiterate, what we're doing here is just taking a simple terminal olefin, thianthrine as our sort of activating group, and undergoing anodic oxidation via electrolysis to generate this mixture of dicationic adducts, which then are pooled up, and then simply turning off electrolysis and adding our amine and base following that to generate these aziridine products. And what we were able to find was that there's actually a wide variety of nitrogen substitution that we can tolerate. And so, for example, we can introduce not only this benzylamine derivative that we saw previously, but cyclopropane moieties and even reactive sites such as an alkyne or an alkene were able to be introduced into these aziridine products. And excitingly also, we could introduce a wide variety of heterocycles, both saturated and unsaturated. For example, a morpholine, we can introduce oxetane, pyridine, so on and so forth. And a lot of these heterocycles are actually quite challenging for some transition metal methodologies to introduce into aziridination reactions due to competitive binding with the metal center. So this is really exciting to us that not only are these interesting for medicinal chemistry purposes, but this is something that our method is uniquely suited for. Additionally, these are perhaps some of the ones that I found most interesting from this method. We can tolerate additional competitive nucleophiles on the amine and still get high yields of these aziridine products. For example, a reactive indole or aniline type structure and even a primary alcohol are still able to be tolerated, and we're able to get selective aziridination in the presence of these competitive nucleophiles, and that was a really exciting find for us. So following our initial foray into the amine variation of this aziridination reaction, we then wanted to see what types of alkenes we could introduce to this reaction to form these reactive dicationic adducts and then carry them forward towards our aziridine products. A wide range of diverse terminal olefins were able to undergo this procedure. We were able to tolerate a good amount of steric profile about that alkene. So for example, this cyclohexane substituted alkene performed really well in this reaction. Excitingly, we were also able to introduce some differential functional groups onto this alkene. A cyano group or an ester. These both performed really well under these conditions. And then we were able to also introduce some functional groups that were more proximal to that alkene. So as an example, this allyl acetate derived aziridine worked really well under these conditions, as well as this phthalimide substituted alkene and this sulfonamide substituted alkene. All of these worked really well, and we were able to observe high yields of these aziridine products. And then another fun one that I really enjoy is we were actually able to tolerate an additional alkene on the substrate. So here we get an aziridine that also has another functional group handle that we can think about doing another reaction with. And we were getting selective aziridination on only one of those alkenes. Following the initial reports into the scope of this reaction, we wanted to see if we could scale it up and start to generate large amounts of these aziridine products. And so we wanted to apply this dication pool method with a flow electrolysis setup. So we did was we took a commercially available flow cell, a Nafion divider to keep the cathode and anode compartments separate, a pump, and then a DC power supply. And then under a constant current electrolysis of 60 milliamps, we were able to only observe 37% adduct. So we were kind of confused, but this is much lower than our batch conditions. And it turns out this is actually due to the electrolyte that we had been using. Whenever I disassembled this flow cell, saw that this Naphion divider had actually started to turn purple due to migration of the thianthrene radical cation across this divider in order to balance the charge. So all we needed to do here was simply change it out for a lithium-based electrolyte. So here the lithium cation is much smaller, and that can selectively migrate instead of this thianthrene radical cation to balance charge, and then leave behind that reactive intermediate that we need to generate these dicationic adducts. And then once we switch from either a lithium perchlorate or lithium tetrafluoroborate based electrolyte, we're able to observe much higher yield of these adducts, and we can also even introduce a higher current in this case and still observe high adduct yield. And so then following these initial results, then we went to actually scale up this reaction on a much larger scale, and we were able to isolate over 3 grams or over 10 millimoles of this N-alkyl Aziridine product. And then really excitingly, we were actually able to recover a large amount of that thianthrene that had been put into this reaction. And so although admittedly, at this scale, the cost of thianthrene here was only around $3 US. So this was really a proof of concept that you can re-isolate this neutral thianthrene. So when going to much larger scales or perhaps going into industry, this is something that we really wanted to show. Following this scale-up reaction, we can take this bulk aziridine that we generated and divert it across some well-known aziridine reactions, such as acetoxylation, azidation, carboxylation, and even aerylation to access some phenethylamine derivatives that are medicinally relevant. Then, following this scale-up, we wanted to show some more synthetic utility of this method. Not only can we generate a natural product in this method via one step, admittedly this is not the most complex natural product, but this I think really drives home the fact that we can take just 2 simple and commercially available reagents to generate a highly value-added product. And then something that I think is really cool as well is we can do our electrolysis under an atmosphere of propane gas and access these really interesting aziridine building blocks with a wide variety of different amine coupling partners. And what this actually let us do is we could take a building block en route to a Pfizer drug that had been previously synthesized via really low-yielding alkylation reaction of this corresponding NH aziridine, but we could do it via instead our propene conditions. So using this very feedstock gas, introduce then this simple amine and get to this drug intermediate and much higher yield. And then additionally, our method, since we can vary this alkene coupling partner, this is highly enabling for the creation of different analogs in a way that this other alkylation reaction wasn't. And we can generate these interesting analogs in very high yield just by changing the alkene. So all this really interesting and diverse utility is enabled by the generation and reactivity of these dicationic adducts. So it seemed to us that it would be really crucial to understand how these are formed under these electrochemical conditions. So when thinking about our electrolysis procedure, we wanted to actually understand what the reactive intermediate in the system was. So presumably, we have a few options here. We could think about either the thianthrene radical cation that we knew we were generating at the electrode via this purple color, but also there was some precedent for this Thianthrenium dication being an active species in some thianthrene literature. So we wanted to understand which of these 2 species is active during this adduct formation. And so in order to do this, we wanted to look at a time course of our electrolysis to observe the conversion of our alkene. And what we see is a really interesting graph. What you can observe here is that we see 2 distinct regions of conversion. And in this graph, there's this upturn of the conversion specifically at 1 Faraday per mole of thianthrene. So essentially, when enough electricity has been passed such that all of the neutral thianthrene that we added into the system has been oxidized. And when this different conversion regime begins, we don't see a corresponding increase in the applied voltage under these conditions. And in fact, what we do see here is that when we compare the potential of this system to the requisite oxidation potentials to access these oxidized intermediates, we see that this potential is much lower than the required potential to access the Thianthrenium dication. Additionally, what we can observe is with the addition of more thianthrene, this second regime, this higher rate of conversion regime, is quite delayed. And we still see that the second regime is still corresponding to 1 Faraday per mole of thianthrene. So when enough electricity has been passed to oxidize all of the neutral thianthrene. What we see here is that by adding more of our promoter, adding more of our thianthrene, we actually have a slower reaction. And so following this time course study, we then wanted to look at the yield of our 2 adducts. And when we did this, what you can observe first is we have nearly a constant rate of bis adduct formation that is quite slow, but then we see a rapid increase in monoadduct formation, again around this 1 Faraday per mole thianthrene point. And so this is a really interesting kinetic scenario where we see high selectivity for 2 different products at 2 different areas of this reaction. So taken together, we believe that these data suggest that there is some kind of disproportionation pathway that is responsible for these 2 different regimes of our reaction. So we believe that this first initial phase, where we have slow, relatively bis adduct formation, is a result of a thianthrene radical cation undergoing some kind of radical addition into the alkene, followed by trapping with another equivalent of thianthrene radical cation to form this bis adduct. However, when we get closer to the 1 Faraday per mole point that I have indicated on these graphs, where that thianthrene concentration is really low, so once we're starting to get to where all of this thianthrene is consumed via oxidation, a unfavorable disproportionation pathway can occur, followed by a really rapid cycloaddition to form the monoadduct. And so here in this case, we're taking 2 molecules of thianthrene radical cation together to form 1 molecule of thianthrenium dication and a molecule of neutral thianthrene. And so in this way, we're regenerating neutral thianthrene that can undergo oxidation at the anode. And so what we're seeing here is no equivalent increase in our potential, but we're generating this highly reactive thianthrene dication, which then can undergo a much comparatively faster reaction with the alkene and become perhaps the dominant pathway here. And so here we believe that the presence of this disproportionation pathway is responsible for the 2 different regimes at both high concentrations of thianthrene as well as low concentrations of neutral thianthrene. So that's where I'd like to conclude my talk today. Hopefully I've been able to convince you that we have a new and interesting strategy for the creation of vicinal dication synthons from alkenes, really enabled via the generation of these highly reactive yet metastable dicationic electrophiles derived from the oxidation of thianthrene. And so we're really excited not only to think about aziridination more and expanding out our aziridination strategy, but also just throwing some other nucleophiles at it. And we really want to access here a general platform for diverse alkene functionalization. And already we've been able to show some initial results into this, kind of accessing this goal. Not only can we undergo aziridination reactions like I've shown you today, but we can also undergo diamination reactions when we omit base, but also dihalogenation reactions with bromide or chloride nucleophiles. And then finally, we've also been able to show that we can get to these interesting vinyl nitrile products via the use of cyanide as a nucleophile. Here we're thinking it's undergoing an addition followed by an elimination pathway to give us these vinyl nitrile products. And so we're really excited by this initial data, and we're really excited to further explore this area and perhaps get to this general platform for alkene functionalization. So thanks for listening, and thanks for having me on. So with that, I'd like to thank the people that helped me out on this project, Diana and Minji, for really getting this project area going, as well as the rest of the Wickens group, and especially the rest of this Thianthrene project team that I've highlighted in red. We have an amazing group here, supported by some amazing undergraduates as well, and I'm really excited to see this area blossom and see where we can go from here. So thanks everybody for listening.
Thank you for tuning in for this Research Spotlight episode, and thank you to Dylan for coming on to talk about your work. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments you have. Follow us on Twitter to stay up to date, and see you all next time.